All right, everybody, we're going to get started here. It's my pleasure to introduce Professor John Mecikalski from the University of Alabama at Huntsville. John is a fellow alum from here. He got his PhD in our department in botany. Is that right?
Well, I got my degree from UW-Milwaukee.
Ah, yeah.
In all atmospheric science, but I took a minor in botany and a master's.
Yeah, PhD from here in 1999 with Greg Tripoli, and even worked at SIMS for a while under George Diak and Alan Wong. I've had the pleasure of working with John for the past many years, working on convective processes using geostationary data. He's been established in many different programs from NASA, NOAA, USGS, NSF, DoD, DOE, mostly focused on using satellite data and how we can best use satellite data to really understand development of short-term prediction of clouds, precipitation, and severe weather. His research has been a part of data assimilation from satellites into models, also looking at solar installation impacts in terms of agriculture. His focus is really generally a lot on using geostationary imagery, visible, thermal, infrared, on understanding how we can use high temporal resolution, 1 to 5 minute imagery, to best understand how we can use these data sets and really get a good foundation of what clouds are doing and why. And so with that, I'll let you take it.
Okay, thank you. It's really interesting being back here. Like Dave said, I've actually was here from roughly 1992 with the Mecikalski group, and that's a software package that a lot of people worked on and no one remembers, all the way to 2004 when I got selected to be a faculty member in Huntsville. So spent a lot of time in SIMS, worked with SIMS while I was through my degree and everything, so it's a really neat experience being back here today. So thank you. This is one aspect of the work I've been involved in. I have to characterize myself as someone who knows a lot about a lot of subjects, but in terms of like being the most expert in any one thing, I think it's been using satellite observations to study cloud dynamics. I did a lot of work with modeling, and obviously I really understand observations. Worked with people close to radar data down in Huntsville, so I've gotten quite familiar with that. But the one thing a lot of people don't really, well, I shouldn't say that. There's quite a large community in NASA that actually does use satellite observations to study clouds. And so the use of the geostationary, the really high frequency observations, is where I've been my focus. That's what this talk's going to be on. This is just pictures I took out of an airplane window. I absolutely I'm hugely fascinated, and I find it very interesting and also equally frustrating when it comes to forecasting convective storms. Huntsville in the southeast United States, we're just about to enter that really humid convective storm regime. If you get into predictability, which I did with my products, good luck trying to forecast the atmosphere more than 30 or 45 minutes in advance. In fact, for a while there in my deeply frustrated afternoon modes when I've yet missed the storm, I'm kind of like, I don't even think the atmosphere knows what it's going to do more than 30 minutes in advance, because I think there's so many small-scale processes that occur that lead, to secondary circulations that cause clouds to form. So I think one of the overall themes of this is, how do you use satellite observations to interpret what the atmosphere is doing? So the clouds are kind of giving you the answer on how much wind shear is affecting their growth, what the instability field is, what's the convergent field, kind of how humid the boundary layer is or isn't on a local scale. So the question is, can you really use the high temporal frequency information to back that out? And then we're coupling it to ground-based observations. And I know this is a long introduction, but kind of the main thing here is these are the science questions, but clouds are everywhere, but it's really, the holy grail is figuring out what goes on inside the clouds. And it's really challenging to get very consistent measurements inside of clouds. And we're not just talking convective clouds, but just any clouds. And they're everywhere around us. So kind of the guiding science questions for this particular talk is, how much of the internal storm dynamics and processes can be discerned from the analysis of satellite cloud top features? Certainly, yeah, we can see the inside of the clouds with microwave, but the resolution is really, really low. So I'm focused on infrared and visible. So can knowledge of internal storm precipitation and thermodynamic processes be gained from analysis of satellite observed cloud top trends? And how can geostationary satellite data be used to inform and enhance parameterization schemes? And this last one is really what's driving the current project I have with Dave Henderson and Jason Atkin in the back room. And so this is also a big focus for the Department of Energy's research. So the talk outline, I'm just going to have it in 3 separate parts. This individual updraft analysis, and it's a bit on the old side. It's something I did back, 8 years ago, but it really guides the current, it's a very good introduction to this talk, and it guides kind of the current work I'm involved in. Another thing, and this is related to the NASA INCUS project right now, is these kind of getting a sense for what the in-cloud updraft structure is. And there's so many factors that influence how the cloud's updrafts are evolving over time and how strong they get. But it's related to how efficiently the clouds are using the instability, aerosol processes, and what have you. So how well can we derive these spatial maps? And then, a lot of this too is, what if you look at ground observations, you're going to get maps of the clouds from the ground and maps of the clouds from the top. So that's really the theme of this. So as you saw in that initial picture, usually a scene of convective storms is made up of a variety of different storm types. And again, these are very complicated pictures. There was a picture I saw at the Department of Energy, kind of a recent paper, I forget the name of it, but it just tried to outline all the different processes in terms of cloud microphysics that go on inside of clouds, that if you actually get a lot of this wrong, you're going to misrepresent and misforecast these cloud scales. And so I think we're all fairly familiar why this is important. This is how clouds are resembled in numerical weather prediction models. Basically, one grid cell often represents many, many clouds. It's a cloud ensemble. And so you're trying to parameterize these different processes. Even our relatively high resolution models, I'm not talking large eddy simulation, I'm talking the operational models. 3 to 5 kilometers, there's still an awful lot of unresolved features. And so bottom line is a poor understanding of cloud processes leads to inaccurate weather forecasts. And the goal there is, again, if you can use our observations, which are available all the time, how could we use that to actually improve parameterizations and kind of inform parameterization schemes? So what can we actually learn? So satellites only see cloud tops. And so again, unless we're using the microwave, we're looking at cloud tops. But however, just that analysis of cloud tops, maybe when I started this work 20-some years ago, I would say that there was only a few processes, but the more you actually look into the details, there's quite a lot of processes. So you got cloud top cooling rates. So I'm going to look at that. If you can find the individual small cumulus clouds and you can track them, and cloud tracking or object tracking is actually a very active area of current research. There's different tracking approaches, but tracking in a Lagrangian sense how a cloud grows can give you, using that, then you can monitor trends like cloud top cooling rates, and that turns into cloud top rising rates. And there's relationships that turn the cloud top rising rates into an in-cloud peak updraft speed. But then, there's other basic research and processes you have to understand, like what influences the rate of clouds top rising versus the how fast that in-cloud updraft is. There's wind shear effects, there's entrainment effects. When you get to the mature stage of storms, you have overshooting cloud tops. I've worked with a prior PhD student, Jason Apke, who now is at CIRA, cloud top divergence. So you're actually seeing the response of these main cloud updrafts in the cloud divergence, the divergence of the anvil. And so you can say something about cloud mass flux. So cloud phase, there's actually, we're talking about cloud invigoration, like when this is all related to late heat release. You get warm cloud, the warm cloud layer, which is unfrozen. You get glaciation, the release of latent heat leads to that updraft invigoration. So the question is, can you actually see signals of that in the cloud top cooling rate? And then you can say something about how does lightning flash rates relate to like what's going on inside the cloud? So again, bottom line is much can be gained from the study of these cloud top features, and you certainly need knowledge of that in-cloud environment, no question about it. So people at SIMS and in this building are quite familiar with these pictures. This is 1 minute data. This is just a random case that I found. But you're seeing, these are obviously severe storms over western Oklahoma. But just in the initiation phase, you're seeing actually quite a lot of information. We see above anvil cirrus plumes, which would be these features here, which give a sense for gravity wave breaking in the stratosphere. The divergence is pretty evident, and then, like I said, if you actually go back to these initiation phases, and I'm going to show another movie in a minute, the degree to which some of these clouds take time to initiate could actually give you information on what the background wind shear is. Is this a rather hostile environment for these clouds to be forming? And most certainly then you can actually look at individual turrets. These are very turbulent processes. Notice the clouds, they grow, but the tops don't necessarily keep growing. They're very bubbling. And this is something we see all the time, but it does point to the fact that these in-cloud updrafts are turbulent. You might have several centers of updrafts. I think some of the latest stuff I saw at a meeting, these updraft cores can be rather narrow. So they're not necessarily thinking about this round cylinder that's going up. It's a lot of more narrow tubes. And again, this is all related to how entrainment from the top of the cloud into the cloud is affecting all this. So again, one of the issues with satellite observations is if you use them, the satellite is broken up into pixels much the same way that a numerical weather prediction model is. So that is for good and for bad. You're getting kind of this average over the cloud, but realistically, how do you turn that average that you're seeing in a pixel to some of the more detailed processes that are going on inside the center of the cloud? So in that sense, like I said, the satellite data fortuitously sort of falls into the parameterization like scales. So we might be able to skip over some steps there, but certainly you got to go back to the basics, and you start to ask yourself, and I'm going to eventually get to this bottom equation here. You start out with factors that affect the vertical motion, the rate of change of vertical velocity with time. And this all equates to some level of buoyancy. We were familiar with CAPE or various varieties of CAPE. But when you actually break buoyancy down into its components, then you have to say, what can you get from remote sensing data that could be discernible? Like if you're getting a signal in the satellite observations, what terms could you be retrieving? I think if anybody, student or anybody could actually figure out how to derive perturbation pressure in the atmosphere, you could probably retire with a Nobel Peace Prize in about 10 years. It is really one of the things you really, really have to probably back out as a residual. It's really tricky. Certainly you can get the temperature excess. That gives you a sense for how the parcel's behaving at cloud top or inside the cloud compared to the environment. You can get some sense for the water vapor. Obviously the temperature of the atmosphere, it's cooling at the moist adiabatic lapse rate, so you can say something about that. And then this QH, which is hydrometeor loading. So there certainly would be a sense for the rate at which a cloud is growing or not growing would be related to how many hydrometeors are being suspended in the updraft. So I know this is way at the bottom, so what aspects of the buoyancy can 1 in 5 minute GOES or geostationary data measure or estimate is the better thing? The shape of the CAPE profile, I think that might be one of them, latent heat release at different altitudes, entrainment, hydrometeor loading, and then vertical momentum flux. And these are really becoming the topic of these new satellite missions. So this is, the new satellite missions with NASA are polar orbiting, so they're kind of limited to these narrow strips with maybe 1 or 2 quick views. When you get to the geostationary orbit, we have, like I said, data very frequently. So this is a study I did. but back in the day, but it really does point to, and this is just the schematic or cartoon of what I did with respect to real clouds, and I'll show the real cloud data in a second. This just looked at, you get cloud top cooling rates, here's your environmental profile, this is just for one day. And then you can basically start breaking the profile into these pieces. You can say that there's a portion of the Cape that was realized based on how much warmer the cloud was compared to its environment. And it's giving some amount of that incremental acceleration. And you could sum up the Cape that's been used to a given altitude above the level of free convection. So basically, updraft acceleration occurs if the air in a cloud is warmer than its clear environment. That's fairly obvious from some of our early thermodynamics. Updrafts would originate from altitude that would be the unstable altitude. Like I said, you could measure this with various forms of Cape, like surface base or most unstable. We're pretty much aware that entrainment limits the instability that's released. So if you're really looking at new cumulus clouds, you know, they go up as these fairly diluted parcels. Things pretty much change once you get to more mature convection, but we're looking at these early stages. So what I did here, and I'm going to just, to some extent, the y-axis is upside down. I had a person in my group go over, he mapped 71 cumulus clouds in 1 minute imagery. This is not tracked, he just actually tracked them by himself. And this happens to be one value. He did this for 71 cases, and after that he came into my office and he says, I'm not doing this anymore, I'm going home for today, because he was being driven mad by doing this by hand. So I bought him a beer and he came back and worked for me. So no, nonetheless, this now with 5-minute data and his automatic tracking methods, this is much, much easier. Like I said, this is upside down. This is the cold end is on the bottom, and so I'm going to flip this into height in a little bit. So 220 Kelvin, so this would be cloud top. 300 or 280 would be near the ground. And so he was able to start tracking this one individual cloud when the cloud's temperature was roughly 281 or 282 Kelvin. What I did here too is I developed a correlation between the rate of increase in an estimate of cloud top rising rate, or cloud top cooling rate converted into a cloud top rising rate. Well, the cloud top rising rate, if you just convert this to height, you're getting a rate at which the cloud is growing in altitude. And you could say, how does this correlate to the amount of Cape that should have been used? And so high correlations are the thick lines, low correlations are the narrow lines. The idea here is if you have these really thin line segments, that might be where the cloud is bubbling. Okay, you might get this leftover turret that's just starting to retreat. Not a lot of Cape was being realized. But here you might have these growth periods of the clouds. And then we hit a point where the cloud rapidly accelerated. So the cloud grew rather steadily. And so you might argue that this was a warm phase, a lot of warm rain processes going on here. The cloud was very likely accumulating a lot of hydrometeors at this point. And at some point here, and I'm going to use 3.9 reflectance to show this, is that because the cloud went substantially below freezing, you would expect it to start to glaciate. And this is this cloud invigoration where the in-cloud hydrometeors freeze. And you get rapid acceleration, and then these are the overshooting cloud tops. Okay, so the cloud overshoots the equilibrium level more than a few times, and this is kind of like sort of what you would expect, but the rate of growth or the trends in the growth are kind of pointing to in-cloud processes. This is when I did the same thing when I looked at 3.9 reflectance. So if the reflectance suddenly switched to a lower value, that points to an ice, so the cloud's top turned iced. And then you have to make the inference that this would be that the inside of the cloud is also glaciating. So you got initial glaciation, a little bit colder than the freezing point, but it really started to completely glaciate. And again, this confirms that that acceleration was due to freezing. Here's where I looked at a number of different clouds. I think this is about 21 different clouds. I flipped the scale here from roughly 2,000 meters above the ground to 13, 14. So these clouds are reaching about 14 kilometers. I normalized it by the time of peak updraft for lack of anything else to normalize it to. So strong overshooting top signatures in all these clouds. Not all of these clouds extended to the same altitude. So this points to clouds here would be, you know, the tropopods might have been lower, it just might have been a less unstable regime, less cape. Some of these clouds grew very rapidly, okay, so that implies wider cape, much more acceleration. So evidence that the updrafts may initially glaciate with unglaciated drafts later extending through the anvil. So in other words, you get glaciation, the cloud might settle a bit, and then with a fast updraft, it turns in, you know, the unglaciated updraft extends to the top. And prior studies have shown that, you know, smaller cloud particles and rapidly accelerating updrafts freeze later. So you're kind of getting that sense of things too. These are for, I think, 11 cases which were supercell storms. And here you're getting a lot more indication of bubbling. Without really anything to back this up, you could argue maybe these environments were more wind shear, you know, there was more wind shear in the environment. And I'm going to show you something that more or less can prove this with some of the dense optical flow data sets that we're showing. So the clouds were growing, but they were also growing in an environment in which maybe the newest turret was getting knocked down quicker, only to be followed by the next one. So the stronger updrafts had delayed glaciation. So there's glaciation signatures, but they weren't quite as highly correlated. So there was some sense, I mean, they weren't as confirmed so much. The lines turned to black, but the glaciation occurred at a higher altitude. So like I said, the rapid growth suggests wider updrafts as compared to the weaker convection, but the intermittent growth also suggests wind shear may have slowed the initial updraft. So like I said, these are all cloud processes that, you know, these would have to be backed up by cloud resolving models, but you could basically take this high frequency data set and start to map out like background thermodynamics and background entrainment rates over regions. And if you could do that, that's pretty powerful just from one data set. This is like a culmination of all 71 updrafts. So this would be like the warm rain phase of the development. That's slower. It's more sluggish because of hydrometeor loading. Here's your glaciation anvil, but you're also getting this overshooting top oscillation. So these are pretty repeatable processes amongst these different updrafts. Okay, so this is just a kind of a summary of what I said, where these are highly correlated. It suggests that acceleration and the amount of cape being used, the updraft is responding more directly to local instability. Where the correlation is low, it's, you know, you're getting influence of intermittent growth, enhanced dynamic entrainment, which is weakening the amount, lowering the amount of instability that's being released. And low correlation between this change in W and change in cape could also imply a period of updraft weakening or bubbling, which is what we see in nature when we look at this. So this study is actually kind of leading to like these updraft maps that I had a study funded partially by EUMETSAT, that just to look at could you take multiple satellite products and effectively make LFC, level of free convection, to equilibrium level updraft velocity maps, focusing on the peak updraft. Okay, so this study was published and it was reasonably well peer reviewed. I'm working on a science paper from this, but I'm actually working on a lot more validation before I finalize this science study, because I do think this would have relevance to. So this updraft algorithm development, this was the goals. It's just to derive an algorithm formed from a combined information from several tested geostationary satellite methods for assessing convective cloud vigor and storm strength. So this is convective initiation. There's an overshooting top product. There's a cloud type divergence product. So none of these are. I think the NASA overshooting top is somewhat operational. None of these are actually quite blessed within NOAA. they could be if one of them might be on the path. So through product fusion, the algorithm provides an updraft focused map at the satellite resolution that increases confidence of updraft presence and better quantify the updraft location, structure, and strength. And I also brought in some theoretical updraft estimates, which are well known in the literature. I think most students who, the theoretical updraft is square root of 2 times Cape. So if you think that is the peak, the question is how close do you ever reach that theoretical maximum? And, not what factors are influencing, but it could actually show up in some of these observations, especially for mature convective storms. There's a lot of science studies that say the cloud top rising rate the in-cloud updraft is roughly half of the cloud top rising rate. Some of these other studies, I was talking to someone here today, I was reminded that if you look at downward directed perturbation pressure, even that could be influencing the fact that, okay, we never reached the theoretical maximum, but maybe we'll get to like 0.8 of that in these mature storms. So these products I brought in, and I'm not going to read all these words because it's going to be too much, but the thing that I really wanted to say is some of these products, the cloud top cooling rate, so this is produced every 5 minutes in my lab, and it's based on this convective cloud mass. So probably about 12 years ago, I developed a cloud mask. Now NOAA has its routine cloud mask, but it's at the infrared satellite resolution. So this one's really designed to be at the visible channel resolution, and it delineates convective clouds of various types. So fair weather cumulus, like you would see outside today, all the way to towering cumulus, cumulus with new anvils, cumulonimbus. And the goal is that you can actually turn each of these clouds types into an object. So when you see a cumulus cloud pattern over a given day, you might have, in one image, you would have hundreds of thousands of objects, little cumulus clouds that you could track. And then these more mature product, overshooting cloud tops. So this is how far the overshooting cloud top extends above the tropopause. So that gives a sense for how fast that updraft was moving when it hit the equilibrium level, and how long would it take that updraft to decelerate. From there, you could back out peak updraft velocity. And cloud top divergence, I did a study with Jason Apke a while back, and we actually looked at radar-derived in-cloud, like if you look at dual Doppler analyses of radar vertical motions, how does that relate to the cloud top divergence? So we came up with some pretty, initial feelings for if you're getting a divergence, and I'll show these divergence fields in a minute, how would that relate to how much mass has to be in that main updraft, and what's the speed of that updraft? And then there's these convective initiation fields, which give a sense for like how, there's other information in here, like the probability of an updraft. And again, here's these numerical weather prediction background environment fields. And I do think a product like this, if you could actually really prove it's going to have value, it would be valuable to the aviation community, the operational weather community, and you most certainly could use this in assimilation studies. Actually assimilate satellite observations via this kind of product to better initialize convective storms. Here's these product. This is the convective cloud mask, variety of different clouds. You see how detailed it gets down in the human regimes. So each one of these little things is an object. This is what I just spoke about with cloud top cooling. Here's the study to relate cloud top divergence to peak updraft, and so you're getting these different pulses, in this case, that actually correlated to peaks in cloud, or increases in cloud top divergence within periods of 5 or 10 minutes. This is this convective initiation product. This is where like I said, these are produced every 5 minutes. You're getting a probability of an updraft at a location, and it's just, look at this, it's extremely busy. So we were taking all these cyan colored objects and treating them as objects and backing out updraft velocities from there, and I'll show you that in a minute. This is this overshooting top field that gives us a sense for where the very strongest updrafts are. Here's the cloud top divergence. This is where this is cloud type divergence. I apologize for not having the units on here, but these divergence, they're order of 1 or 2 orders of magnitude above what you get on the synoptic scale. There's information here related to above angle cirrus plumes. I don't have that in there, but it's correlated to these updrafts, the overshooting tops. So, like I said, many satellite products that are available that effectively are giving us proxies for the in-cloud updrafts. So let's try to combine these. This is the other thing that we're doing. This is this dense optical flow. And so what Jason Apke did, and I probably could spend 10 minutes talking about this one product, and I'm not going to do that. But this is actually taking dense optical flow wind speed and turning it into a color. So you're actually getting a sense for these particular cumulus clouds. They're telling you, because they're not initiating into storms, they're giving you a sense for, well, certainly maybe there's not enough low-level convergence, but the rate at which they're dissipating is giving you an indication of how much vertical wind shear and how much entrainment they're encountering, such that convective initiation failure is actually happening. And so that's information that is not yet part of this updraft product, but these are basic research-based, you could use these products to start asking some really good basic research questions. Again, the clouds are informing us of what's going on in the environment. This is the methodology. So what I did here, I broke this into a pre-convective and existing convective product, which I overlaid, and I'll show you that in a minute. So pre-convection is these young cumulus clouds. They're active, haven't yet reached the tropopause, and of course existing convection has this very nice overshooting top, a large anvil. And the one thing with satellite observations in the infrared, as we know, you can't see below cloud top. So anything that's masked out by the anvil, unfortunately, is not going to be part of this figure. So I wanted to show this. This is how these products are being used. I know there's a lot of words, but promise there's figures to come. These are the cloud types I'm focused on. Current cumulus, cold water clouds, cumulus, warm water clouds, and cirrus covered cumulus, which is the beginning of a new storm, so the first anvil. That's from the convective cloud mask. You got cloud top cooling rate versus CAPE. I mentioned that in a minute. You can actually take the cloud top cooling rate, turn it into a cloud top rising rate, turn that into an in-cloud updraft estimate. That uses some prior studies, prior theoretical studies. You could use, you could just see how much if you could just take a ballpark and say, if I look at most unstable CAPE, and I said 50% of the most unstable CAPE was being used for the updraft, you come away with an updraft estimate that way. So you're getting multiple estimates. This is this cloud top cooling rate. I talked about that already, and that's related to this peaking cloud updraft. Overshooting tops again. Question here is how high above into the stratosphere is this extending? So if you know something about lower stratospheric stability, you could say if I have an updraft that hits the equilibrium level at 45 meters per second, how long is it going to take to decelerate? And the depth of that overshooting top, given the background instability, there's enough information there to derive that peak updraft. Cloud type divergence, I just mentioned something about that. And I looked in the lightning flash rates, but admittedly there's very low direct relationship between how much lightning is produced and peak updrafts. It's more related to updraft volume. So here's this one case I looked at, and this is really this is a generic day in the southeast United States, so nothing special. These are these two maps. So this is a combined updraft map. I'm going to show a visible image here in a minute. So these darker areas, which are more or less the anvils, this is where you're getting updraft information from the cloud top divergence field because it's covering a larger region. There's some of these smaller dots in here you can't quite see. That's where the overshooting top information is coming in. These areas of weaker updrafts, roughly 5 to maybe 12 meters per second, that's coming from the cumulus cloud field. So this is starting to look like something you would expect to see. And again, obviously it compares directly to the satellite because the data are coming from the satellite. But you're getting maps related to where the clouds are. And so, you know, again, if you were to look at this, these red areas, sorry, these yellow areas with the weaker updrafts, these would be the smaller clouds, and you're getting these darker areas, which would be more or less these medium-sized towering cumulus clouds. This doesn't have the overshooting top part, so that's why this is all not filled in. That particular map doesn't. So what are these? These are updraft velocities in meters per second. So it seems like, you know, this would ideally be if you flew a plane through these clouds, this is what you would experience. This is another case. This happens to be a nighttime case with extremely large cape. Produced prolific lightning. I did this as a complete contrast to that other case because it really couldn't, it used different components of the cloud product, focused on the use of cloud top height as a derived product to bring this in. Now there's not as much small cumulus in here because a lot of the small heat-driven cumulus aren't really something you would see at night. But you know, it was a proof of concept that you're getting some decent vertical motions. I actually did a case number 2 that was for some very strong storms in Oklahoma, and my retrievals came up with something like 45 meters per second, and I was thinking that's just way off the mark. And then I ran a WRF model simulation, and I was getting updraft speeds that happened to be, in that case, 48 to 50 meters per second. So at least this project, admittedly, I went into this with a heavy degree of skepticism that something like this would work. Because if you really wanted to make it work, you could tune the knobs to make it work. And with not a lot of tuning, and I promise you I did not a lot of tuning, it seemed like on like a first order and even a second order, it worked out pretty well. And so now, again, I'm going back and doing more validation data sets. This is a comparison to the WRF simulations. So I was actually getting, now the one problem with the WRF is I'm not getting a lot of small clouds. But for the medium and larger clouds, it seems to be producing updrafts with relatively the same magnitude. Of course, you're not going to be at the right place at the right time. This is the updrafts I was getting from that simulation. You see these peak updrafts here were upwards of 35 to 40 meters per second. So that is, and it was consistent with the cape. So you could actually argue, in these cases, in these cores, I was maybe like 0.7 to 0.8 times the cape being used. And that starts to go back into theory. And this is just a PDF of the same thing. The satellite on the good news side is giving us a really good, you know, it's giving us what nature would say in terms of cloud distribution. It's tending to have kind of this trimodal distribution where you're getting lower velocity, smaller clouds. You're getting maybe a towering cumulus phase where if they reach some point, they really start to accelerate. That could be where the glaciation first occurs. And then in this case, it was picking up a very small amount or smaller amount of clouds that were making up the really intense updrafts. And that I'm going to guess here is where the overshooting cloud tops were particularly tall in this case. Okay, so that's kind of this long background to the current project, and I just have a few more slides to show. This is the project I'm involved in with the Department of Energy, our Mobile Facility 3, which has just been very nicely stationed in North Alabama. There was, it turned out they wanted to put that site there like they have the Southern Great Plains site in Oklahoma, to study the really challenging land surface, atmospheric interaction, and convective cloud processes that occur in the humid southeast and eastern United States. Like those regimes in weakly forced convective environments, they're really challenging. We end up with many, many days in the summer, and this is where I just want to pull my hair out, but it keeps growing back, is 38 to 40% chance of rain is like completely meaningless. I mean, what do you do with that? Every single day, over and over and over. And yet you know someone's going to get 1 to 2 inches of rain. And it's going to happen again and again and again. And I sit there and I'm trying to figure out, well, it rained here yesterday, so I should get rain at my house today. Nope, it rained there. So what'll happen is multiple places will get rain on the same, say, 2, 3, 4 days in a row. in other places we'll get nothing. And so there seems to be quite a linkage between land surface processes and soil moisture and evaporation and where the clouds form, and that's partly why the ARM site went there. So this is the Mobile Facility 3. Turns out UAH is where that UAH swirl is in the upper right of this figure. It's nicely coordinated with the weather facilities we have there, but it's got a C-band radar that's a bankhead. Central facilities got these satellite sites that are going to provide additional information. The site is heavily forested, but it's actually partially farmland too. It's kind of a national forest, but some of it's actually used for other things. So when we wrote the proposal, these red highlighted sections are really what we are focused on: processes that regulate shallow to deep convective cloud transitions, relationship between boundary layer and coverage of convection, and the nature of convection updrafts, including size and intensity. So how does all of this fit together? The science objectives we worked on, there's actually a lot of words here. My group down there in Huntsville is focused on these first two, and it's very much related to if you can map clouds from above and clouds from below, what are the thresholds for which you get a shallow cumulus cloud deck that might have a few breaks that'll tip the scales into something of towering cumulus, and then what happens when some of those towering cumulus go on to make new thunderstorms, and how does that relate to like cloud-based vertical motion? These lower two science objectives are going to be done here at the University of Wisconsin. So the guiding science questions here is really, can retrieve cloud-based height and cloud-based vertical velocity data be used to trigger deep convection? So could you actually, this is a study that my former PhD student worked on, like, could you actually relate it to trigger function parameters? If you could, like, could you derive trigger function parameters that incorporate satellite observations, and how does that compare to trigger function parameters that are being generated by something like a low resolution WRF model? How well can we quantify cumulus cloud updrafts of the cloud depth? So this brings in my prior updraft research. So cloud depth being cloud base, say the middle of the cloud and near the upper parts of the cloud. And then what are the statistical distributions of cloud parameters as related to cloud growth and evolution and to convective initiation? So like I said, I'm using the prior research here really briefly to just show what work has been done to date. The newest AMF3 data are going to be collected this summer that we're going to be able to start to use, so I can't show any of those results. But I can show a couple slides left related to this trigger function variable. So what my student did is he actually looked at VIIRS. We really only wanted to look at the highest resolution satellite imagery. So we focused on the use of VIIRS, which was 375 meters. We wanted to get kind of the warmest cloud, convective cloud pixels, which should be related to the level of free convection. So, you know, when the cloud first, when you first get condensation, that edge of the cloud, the warmest edges of the cloud should be related to the cloud base temperature. So if you know the cloud base height and you know the cloud base temperature, that was actually a big piece of the trigger function, is where the cloud formed. So we were after getting cloud base height and cloud base vertical motion. So we brought in this, he made a enhanced convective cloud mass to get at the smallest, warmest clouds. We used the Doppler LiDAR at the ARM facility to confirm the cloud-based height observations and to gather cloud-based vertical motion statistics. He actually used radiosondes to convert cloud-based temperature to cloud-based heights. And of course, you know, we brought in environmental information from the models. So what he did do is he had two retrieval methods, one for cloud-based height and one for cloud-based vertical motion. And these are all from remotely sensed observations. And the next thing was then to be like, if you had a trigger function in a model, how does the results we were getting from observations compare to what we got from the model? So The Kane-Frisch scheme is widely used. This is from the WARF model, so it's a convective parameterization scheme that just determines if you're going to trigger in a given grid point. I'm not going to go into that much of the detail, because that in itself is a long conversation. But basically, it finds an updraft source layer per pixel, and it tries to calculate the mean thermodynamic characteristics such that you're trying to find out at what point would a parcel be warmer than its environment, and it therefore would go on to accelerate and make deeper convection. And the trigger function is actually rather simple. And what my student and I were after is this delta t parameter. So you have a parcel, and you're asking the question, is the parcel going to be warmer than the environment? And if the parcel, this delta t gets to be a certain value, it's either triggered if this is warmer than the environment, or it's not triggered if it's the otherwise. So what goes into this delta t parameter? Turns out this threshold vertical motion, which is this W naught, related to the level of the lifted condensation level, which is related to the cloud base height, is actually a big part of this term that actually dictates this delta t. So we're actually able to connect, again, observed values of these two parameters to something of a trigger function and derive these trigger function values over this domain. We looked at these different regions. This is the Southern Great Plains region. We didn't have AMF3 data, so this is what we did. And you actually find out that these values, the delta t values, were coming in pretty close to what we, what I'm not showing here is how they validated against WARF, but they actually were quite close. So the question is, and this is where this work is now, the paper that came out just proved the concept. The paper that's coming out next is going to compare this to the WARF model. You cannot directly assimilate these. I mean, we're not doing that in this particular study, but if you could, realistically, you could have maps of these trigger function variables that, let's say you could produce these things every few minutes. Could you actually trigger convection at the right place at the right time in the model? So that was kind of the long-term goal of this thing. So, yeah, so with that, I think I'm nearing the end. Oh, and this is the last thing that I did related to the AMF3. So we took what we did there with the cloud-based vertical motions. You're getting relatively small vertical motions near the cloud base. And again, these are the cloud-based vertical velocities are derived from the combined satellite and ground-based observations. This is a KAZ radar. It's an upward-looking Ka band radar over the arm sites. So you're getting lower parts of the cloud. And then this is the cloud top cooling rate from GOES. So in a sense, you're starting to build this vertical momentum profile, or vertical motion profile, through these small clouds. And this is the database that we want to go on and form. So with that, this is my conclusions. Selfishly, I'm trying to kind of build this into, get ahead of this NASA INCUS project, such that, that NASA INCUS is polar orbiting. Would be very, very nice to have updraft velocity estimates that could actually corroborate some of the data sets that are going to come out from INCUS. Big goal now is to collect maybe 1 to 2 good years of data over the AMF3 and work with the collaborators at UW-Wisconsin. I continue to work on validating the updraft with large eddy simulation resolved models like the WARF. And the last thing I want to make is when we go to this GeoExo, this is next generation GOES, we're going to get fine enough resolution in the infrared that's going to actually kind of make nighttime and daytime updraft, cloud resolving fields better. So the future, as we get the higher spatial resolution, is that what we've done now should actually be more resolved. So with that, thank you very much again for having me. It was really good to share all this work.
All right, thank you, John. Let's open the floor to questions, and as normal, we'll start with students first. Do you have any questions for John?
Hi, I'm just wondering what resolution you run your simulations at.
for validation.
Yeah.
Yeah, I mean, right now I got a 250 meter resolution wharf simulation running. 1 kilometer resolution seems to be good enough. I think 500 meters is probably where I'm gonna end up. 250 meters, just the computational time and the domain sizes are too small. So I think I can run it at 250, but as you get to higher resolutions, your domain size just gets smaller. So, and I'm after looking at populations of clouds. Yeah.
Do you have any thoughts as to how that trigger function would change relative to the grid spacing on the model that you try to implement it?
Yeah, that's a really good comment. That trigger function's optimized for roughly 25 kilometer grid cells.
Yeah.
So even though we did things at a higher spatial resolution, we back things out as if it was a 25 kilometer pixel. So those updraft vertical motions, those cloud-based updraft velocities were not very big, 1.5 meters per second. That's because it's a 25 kilometer average, 25 by 25 kilometers. You can go the other way around. If you do get down to 3 or 12 or 13 kilometers, you can normalize, you can adjust things to those scales. I just didn't talk about that here, but that's a good point. I'm glad you brought that up.
Okay. Open the floor for anyone.
You suggested a qualitative range of maybe 10 to 20 meters per second for medium updrafts. I was wondering if you thought at all about the same idea for diameter. Do you have a qualitative estimate of typical diameters that would go along with that?
Oh, the updraft diameter?
Yeah.
No, I haven't thought about that. In fact, the low, medium, and high values were suggested as the challenges of getting an exact value, one may never know. So they suggested this low, medium, and high. And the argument would then, how wide would those updrafts be? And that's something I really, I could take a swing at that if what's the width, what's the size of the overshooting cloud top in terms of the diameter? But that, I think I would only do that for mature convection. I think that's an open research question. Yeah.
For verifying updrafts, you showed the figure that has the 3 different levels of the atmosphere depending on what instrument you're looking at. Is there any potential to do dual Doppler analysis with the C-band with potentially like a nearby next red, or is it too complex of a region to?
No, one of the real point of doing this arrangement here, the baseline between these 2 C-bands is, I think, roughly 40 kilometers. So it's ideal for doing, that's why they cited this where they did. So we got a really nice dual Doppler lobe here. They were actually going to put another phased array radar here. So arguably there would be multiple dual Doppler lobes in this region. So for the next maybe 5 to 8 years, that was the idea, is you would oversample this area in terms of radar, such that and there's a Columbus, Mississippi radar here, so that's, the baseline's really long, but I think the goal is that, yes, you would have really good dual Doppler coverage.
Any other questions?
I guess my question, John, is related to Matt's. If you had to lay out a matrix in your mind of updraft diameter and updraft strength, would it be dots all over that space, or would there be sort of clusters, and would those clusters relate to certain storm environments, do you think?
I think there'd be clusters.
Yeah.
Yeah, I think if you get the rotating updraft regimes or the squall line regimes where you get these narrow, vertical updrafts, those would be 2 well-defined regimes.
Mm.
And I think the other regime would be the narrower updrafts of new convection. I think where it would be dots all over the map would be these towering cumulus, because you could get towering cumulus in really hostile environments where the updrafts might be these really arduous looking turrets.
Yeah, and they're getting sheared off the top or something.
Yeah,
That's
and
one
then
example.
if you get the low shear environments, like in humid southeast or whatever, tropical, they might just be more vertical.
Yeah, okay.
That'd be just my guess.
Hmm.
So,
Any other questions? All right, with that, let's give John one more.